So yeah, I'll be talking about reducing liveness to safety in first-order logic. And this is joint work with Jochen, Hoenicke, Giuliano, Losa, Andreas, Podelski, Mooly, Sagiv, and Sharon. So first, I want to mention briefly what are liveness properties that we're interested in verifying. And liveness properties are, unlike the more usual safety properties, they state that something good should eventually happen. So an example of a liveness property is non-starvation. You want to prove that in some mutual exclusion algorithm, every thread would eventually get to the critical section, or that your algorithm would eventually reach some good state. And it's typical for liveness properties to depend on fairness assumptions. For example, that every thread is scheduled infinitely often, or that messages are eventually delivered. And our contribution in this setting is a technique for proving liveness and temporal properties in general of infinite state systems that does not use ranking functions or reasoning about cardinalities or arithmetic. Instead, we use only pure first-order logic. And really, the benefit of this is that we can get more automation. And in many cases, we can even reduce the reasoning to reasoning in decidable fragments, such as EPR. And then the verification conditions are checked decidably. And this formalism, really, we can handle both infinite state per process and dynamic spawning of processes. And we've applied it to some interesting distributed protocols. You see here some benchmarks. For some of them, we have the first mechanized liveness proofs. You see that the verification times are quite low. And really, there are objects there that really need to be considered infinite and not just parameterized. OK, so before I'll explain you our technique in more details, I'd like to give you an illustration of really the key idea. So if we were in the finite state setting, we could prove a liveness property by considering only ultimately periodic traces. So proving liveness, I guess many of you know that it boils down to proving termination. And if we have an infinite trace in a finite state, then it must eventually visit a state that it visited before. So really, to prove that there is no infinite trace, we have to prove that it's enough to prove that there is no lasso. And in the finite state case, it's really an if and only if. When we go to the infinite state case, this breaks down, because you could have an infinite trace that never visits the same state again. Now, one way to mitigate this gap is to just introduce a finite abstraction. And then really every infinite trace should visit some abstract state twice. So we lose the if and only if, but still if we manage to prove that there is no lasso, then we can prove our liveness property. But the problem we might get, so say that this system actually is terminating, there are no infinite traces, we could still get spurious lassos. And in the many systems of interest, this is really what happens when you introduce a finite abstraction. And our idea to mitigate this gap is something we call the dynamic abstraction. And the idea is that the abstraction is dependent on the state of the system. So maybe in the initial state, we would have a coarse abstraction. When the system takes a transition, the abstraction gets refined. When it makes another transition, it gets more refined. Another transition, even more refined. And of course, we have to somehow decide when to stop this process and freeze the abstraction to maintain soundness and say that, OK, now we're not going to change the abstraction anymore. We're going to let the system keep running. And if we manage to prove that there is no lasso in this setting, then it is sound, and we have verified the liveness properties. And you see here that really the finer abstraction managed to distinguish, to get rid of this spurious lasso. So to show this in really more details and how the point of first-order logic comes into play, I want to introduce this example that I use throughout the talk. And this is a very simple protocol for mutual exclusion. It's called the ticket protocol. Some of you may have seen it in a VMKI keynote as well by Azadeh. And every thread follows this control flow graph. It has 3 states, idle, waiting, and critical. We have 2 global variables for the next ticket and the service number. And every thread has a local ticket number that it's currently holding. And if a thread wants to go into the critical section, it atomically increments n and stores its previous value in its local variable. Then it stays waiting as long as m is greater than s. And once the service number is greater or equal to m, then it goes into the critical section. And on its way out, it increments the service number so the next thread can go into the critical section. And what we would like to prove about this protocol is the liveness property of non-starvation, namely that it's global for every thread. It's globally true that if it's waiting, it would eventually go to the critical section. And so I want you to think of this protocol in a setting where threads can be dynamically spawned. So in an infinite trace, we could have infinitely many threads being spawned. And this liveness property, of course, depends on the fairness assumption that every thread is scheduled infinitely often. Now, in order to prove this property under this fairness assumption, we really want to prove that for an arbitrary thread we call T counterexample, there could be no infinite trace that satisfies this formula, that every thread is scheduled infinitely often, and this counterexample thread eventually reaches a state where it's waiting, and it's never in the critical section. So the more classic way to do this kind of proof is to give a ranking function that has to decrease infinitely often on every trace that satisfies this, and this really shows that there could be no infinite trace like that. And you could do it for this protocol, but you would really have to reason about thread cardinalities and arithmetic, and this would also get mixed in with quantifiers that describe the behavior of the protocol, and then the reasoning would require, it would be much harder to automate. You wouldn't even have a complete proof system. And to avoid these difficulties, I want to show you a technique where you can prove this property, but only using pure first-order logic and even a decidable fragment in this case. So let's be a bit more formal about this process, and we call it first in the finite state system. So in the finite state case, we start with a finite state transition system and an LTL property, and we want to prove that the system satisfies the property. We perform the so-called product construction to construct a Buchi automaton that really every trace accepted by this automaton is a trace of the system that violates the property. So to prove this, we now need to prove that this automaton is empty. It has no infinite fair traces. And really, we can lift this idea of cycle detection of lasso counterexamples and only consider, to show that this is empty, we just show that it has no lasso in its language. And we can really reduce this to a safety property by having a transition system that guesses the start of the lasso and just an assertion that you never visit the same state after seeing all the fairness constraints. So let's try to generalize this to the infinite state case. So the first step actually generalizes quite well. You can express your transition system in first-order logic, use first-order linear temporal logic to express your properties. This is what we've done before. And the product construction works. You can actually create a first-order Buchi automaton that it would be empty if and only if the system satisfies the property. But the second step, of course, completely breaks down because it's not sound in an infinite state system to assume that if you show that there is no lasso, then really there is no infinite word. And for the ticket example, this can happen for two reasons. Either a ticket number can grow unboundedly. So you see even the state of every thread is infinite. And also, really in an infinite trace, you could have infinitely many threads. So even if you came up with some finite abstraction for every thread, still it wouldn't solve the problem. Okay. So now our solution to this problem is really taking advantage of the way we represent things in first-order logic. So I want to explain that. So we represent the states of the system as first-order structures over some vocabulary. And for the ticket example, the vocabulary includes 3 unary relations to represent the program counter of each thread, a function from threads to ticket values to represent the local variable, and 2 global constants, n and s, to represent the global variables. And we can express both the initial states and the transition relation as quantified formulas in first-order logic. And we can depict the states of the system with these tables. So you see, for example, this is a state where thread T0 is in the idle state, T1 and T2 are in the waiting state, and T3 is in the critical state. M is captured by this table, where the ticket number of T0 is 0, of T1 it's 3, T2 it's 2, and so on. And the 2 global constants are also depicted in this table, where you see that n is 4 and s is 1. And really, these tables are infinite, because we have infinitely many ticket numbers and potentially infinitely many threads. And as we've already mentioned, coming up with a finite abstraction is going to be a key ingredient to our approach. So really a natural abstraction for a first-order structure is to project it to a finite set of elements. So say we fix some finite set of elements D, which includes the 3 threads and 3 ticket values. We can now just look at a finite subsection of these tables, and this is, of course, finite state. You only have this many finite ways to put values in these bits to arrive to a finite projection of this state. And we would denote this operation by this projection. And really, we could attempt to use this to get a sound proof for the ticket protocol. Namely, we would find some fixed set D of threads and ticket values, and then we would try to prove that you cannot have this abstract cycle where you visit 2 states and that have exactly the same projection to D. Now, this is sound, but it's going to fail even for this simple ticket protocol. And the reason it fails is because if you give me some finite set of threads or ticket values, I can arrange for a counterexample where the ticket values grow beyond anything you have in your finite set. And then you would, of course, have this abstract cycle. So you would have spurious abstract cycles, and we can do a similar thing with spawning new threads. So the way we solve this, we get rid of these spurious counterexamples, and we get a technique that does prove the ticket protocol and the other protocols that we also considered, is that we do not fix the finite set D globally, but instead we have a mechanism to set it per trace. So I'll first explain this in the ticket example, and then I'll show you the general construction. So for the ticket example, we have this counterexample thread that we know it should go to its waiting state and then never reach the critical section. And we wait until this thread actually goes into this state, and only then we fix the finite thread D. And what do we fix it to? We fix it to all threads and ticket values that we've seen in the trace so far. So in every step of the trace, only 1 thread is scheduled and maybe a few ticket numbers are involved. So after a finite prefix, this set will be finite, and we can use it for the finite abstraction later on. And then if we manage to prove that we can't see this situation when we have 2 states that have the same projection to D, then we can prove the Liveness property. And for the ticket example, it really works. So now I want to explain the more general construction. So in the more general setting, we have this first-order Buchi automaton that is expressed by a formula for the initial state, a formula for the transition relation, and the Buchi acceptance conditions are first-order formulas with 3 variables. And these 3 variables are really essential because, for example, you want to say that every thread is scheduled infinitely often. You would express it by this formula with a 3 variable, and the semantics of it is that for any assignment to the 3 variables, a fair trace should satisfy it infinitely often. And now to lift this structure for a way to define this finite abstraction, we define the footprint of the initial state and the footprint of a transition. So the footprint of the initial state, say we have some constants C1 and C2 and some existentially quantified variables. The footprint of the initial state would include the interpretation of these constant and existential variables at the initial state. And it's a finite set of elements. Similarly, for every transition from S to S prime, we define the footprint of this transition as the interpretation of the constants and the existentially quantified variables here at the post-state of this transition. And remember, we also have these Buchi conditions with 3 variables. So now our canonical technique for defining this abstract cycle is that first we would wait to see all the acceptance conditions only on the elements from the footprint of the initial states. Then we would freeze our abstraction according to the footprint of all of the transitions we've seen so far. And this would be a finite set. And then we would detect cycles where we visit the same 2 states, S1 and S2, that have the same projection to this D, and also that between them, we've seen all the acceptance conditions for all the elements in D. And the claim is that if we prove that this cannot happen, then really there could be no infinite counterexample. So the Liveness property holds. So here we start just with the footprint of the initial state. As we make more transitions, the footprint increases, the abstraction gets more refined, but after the fixed point, it really stays the same. So I want to outline the soundness proof. It's actually quite simple. So we want to prove that if there is no abstract lasso, which we defined in the last slide, then there is no infinite counterexample. So say we have some infinite counterexample. It starts at some state. This state has a finite footprint. And because the trace is fair, after some finite prefix, we would see all the fairness constraints on this finite set. We will call this state SF, the freeze point. And now we will denote by D the footprint of all of these transitions. This is also just a finite set. Now, because it's a finite set, and this is an infinite trace, there should be some infinite subsequence that all of its elements would have the same projection. So the first one of these, we can call it S1. And now from S1, after some finite prefix, we must see all the fairness constraints on this finite set D. And then this element, the next one, which has the same projection afterwards, and it has to exist because this is an infinite subsequence, this would be our S2. And what we've really constructed is an abstract lasso. So you see that if now we prove that there is no abstract lasso, it would mean that there is no infinite counterexample. And this can really be used to reduce all of the problem to a safety problem in a first-order transition system. And we do this by just engineering a monitor that tracks this property. So you see that it would start in this watching state. After the freeze point, it will move to this state in which it's frozen. And then it will stay in the saved state where it copied the previous state. This would be with a non-deterministic guess to guess where this S1 is. And it would go to its error state if it's seen a state that has the same projection. And this can really be implemented in first-order logic. We add relations for tracking D and for keeping track of the Buchi conditions that we've not yet seen, and also a second copy of the vocabulary to remember the previously visited state. So now I'll briefly show you how this works for the ticket example. We want to prove this property. And let's say that the T counter example here is T0. So we add this monitor. This means we add D for the footprint we've seen so far, and B for the Buchi conditions that we're still waiting for. And in the initial state, we would initialize both of them according to the footprint of the initial state. So we would have only T0 because it's pointed to by this constant, and the ticket number 0 because it's pointed to by N and S, the global constants. And now let's say that T1 would make a transition. So it would go from its idle state to its waiting state, and it would also get inserted into D, and also the ticket number would bump and get inserted into D. Let's say now that T0 would take a step, so it's also going to go into the waiting state. And now, because we've seen the Buchi condition for thread T0, it's been scheduled, now B is empty. We removed it from B. So now we can go from the monitor can go from the watching state to the frozen state. And it can even go another step to the saved state, because this is just a non-deterministic. So in the interest of time, I'm taking it now. And when we make this transition, we copy all of our state to a saved state, a shadow vocabulary that we have here. And we reset B according to D. So you see that both T0 and T1 are now in B. We're now waiting for them. And now we're going to monitor this condition. Is it the case that B is empty and the finite projection defined by D is the same between these two states? So now we won't go to the error state because B is not empty. We can schedule T0, which would just do nothing to its state, but it would, because it's still waiting to get it for S to increase, but it would get removed from B. If we would now schedule T1, it would go into its critical section and also get removed from B. At this point, B is empty, so we might go into the error state. But notice that it won't happen because we see the difference between this state and this state in our finite abstraction. And really, the key thing that made it work for this example is that once a thread is waiting to enter the critical section, it only depends on the threads previously scheduled. Now, another point that I really want to stress is that we haven't done a finite abstraction of our transition system. It's still an infinite state system that we're trying to prove safety of. we're just using the finite abstraction for the lasso detection. And because it's an infinite state system, we have to now use an inductive invariant to prove that it can never go into the error state. And this is our inductive invariant for the ticket. You see, it's not that scary. It really has two parts, one that shows that the abstraction is precise enough, and the other that really points the difference between the current state and the previously saved state. Now, this doesn't always work. If say, a thread could stay in the critical section for a non-deterministic number of times, this simple reduction would fail. In the paper, we also use something we call a nesting structure to increase the power of this, and I won't go into this due to the interest of time. I do want to mention that this reduction is incomplete. A reduction from liveness to safety really cannot be complete because they have different computational complexity. But the interesting sources of incompleteness are first the form of the reduction, and also the use of first-order logic means that maybe just the way we define the abstraction, it's going to lose completeness, and also it could be that the reduction was complete in the sense that the resulting system is safe, but still you have no first-order inductive invariant to prove safety. And in the paper, we give some examples of these. I'll briefly mention our experimental evaluation. We implemented this in Ivy, which internally uses Z3. You see that we've applied it to these distributed protocols. Some of them, it's the first mechanized liveness proofs. And really, the interesting thing to note here is that in all cases, but this TLB should done, the verification conditions were actually in the decidable EPR fragment, and the verification times are really short. Another interesting point is that how complex is the invariant you have to come up with to prove liveness. So we compared it in terms of number of conjectures that were manually provided compared to the one we used just to prove safety of these systems. So you see it's a bit more because it has more moving parts in the liveness proof, but it's still very manageable. I'll skip this, I think. And just to wrap up, we've seen a technique for using only first-order logic to prove liveness properties, and this is really surprising. First-order logic is usually considered weak, and in the future, we hope that this would allow more automation because we would be able to lift techniques for automated safety verification to prove liveness. So thank you for listening.
Let's first start from an online question. I guess you have a slide explaining the method is not complete. I think the question is, can you characterize the liveness properties that you can't adapt to safety property?
So
what kind of liveness property that you can adapt to safety?
That you can or that you can't?
You cannot.
So in the paper, this is a very interesting question. So in the paper, we have some attempts to show examples, for example, where the number of steps you have to wait is a non-primitive recursive, then this approach would fail. But we don't have a complete characterization of that. That's a very interesting question. Okay. Sorry.
Can I see a last question? Can I see a last question? So the numbers in so the numbers like you showed how many seconds, right? So
yeah.
That's basically you have to provide the verification conditions, right, manually, you know?
Yes, so it's a deductive verification approach. After the reduction, the user provides the inductive invariant, and the times were just for checking it.
So you basically implemented the reduction, and then the verification. So you have to provide the verification condition manually on top of that afterwards. Yeah, is that right? Yeah.
Yes, you provide an inductive invariant.
One last question.
Hi. So I saw that in your benchmark you use some kind of the consensus protocol like a PAXes.
Mm-hmm.
So I'm wondering that how you make sure about the liveness when there is some failures applying for the like a failure for the thread executions in the like a PAXes protocol. How you can apply? How you can ensure that the liveness will be preserved with your strategy?
So you're asking how come I prove Paxos live because it's not live?
No, because if there is some failures, because the failures is a common problem when you apply this consensus protocol in distributed manner, okay? So how you can ensure that liveness when you have failures of the threads,
Yeah, so the liveness that we proved is under fairness assumptions that ensure that eventually there is a quorum of nodes that can communicate with each other. And this is the best you can hope for consensus protocol. So it's under fairness assumptions that we took from the paper that introduced the protocol.
So you mean that you assume some kind of the crash recovery models in your system? Even if one thread fails, so you assume that you will recover, you will start execution again at some point.
So as long as there is still a quorum of threads, still a majority of threads operating, the protocol can reach consensus. And we take this as a fairness assumption, basically.
Thank you.
Let's thank our speaker again.